Cool, thanks. All right, so let's go ahead and do these demos. But before I show the AutoML demo, I want to kind of contrast it to the Vision API that I was talking about earlier. So what you do here is, I'm just going to do a quick demo of this. I'm going to get this image of a cloud, upload it here, and this is going to do some labeling on the image. It's finding that this is an image of a sky and grassland, 97% cloud. The problem here is it's not making it very clear what type of cloud it is. I mean, I can scroll a little further down and it says cumulus 85%, so it has some idea of what kind of cloud it is, but maybe for this use case, what I care about is only classifying the different clouds between 5 or 10 different cloud categories. Maybe I actually don't care about sky or grassland. So the Vision API is good to annotate your image, but it's not. It can also do things like this, like dominant colors. It can tell you if it contains adult images or medical images. You get this JSON type of result back with cloud and its score. This type of cloud, it's about 85% sure about. Okay, so this is the Vision API. Let's check out the AutoML Vision API. So what we're going to do here is we want to actually classify images for 5 different types of clouds. So there are 2 essential, basic things in AutoML Vision: datasets and models. Let's start with datasets first. So I have a few different datasets here. The one we're going to look at today is called the Clouds 2 dataset. I have about 1,820 images that are labeled in this dataset. So let's actually go look at the data. Here are the different 5 different categories or classes and how many images I have for each. We can go look at one of these, maybe we'll look at the cumulus one. So these are some sample images of the cumulus type of cloud. How did I even get this data in there? Well, here's what we did initially. You go to import, and then you can import a CSV file from Google Cloud Storage that kind of says where all the data is. Here's what it looks like. So here's a sample CSV file. It basically just has the location of the image, and this is the label. So here's how you can format your CSV file. You can basically say what label it is. You can also put train, test, or validation at the beginning of each line to separate out your different data sets, and then just pass that CSV file in. You can also upload images directly, and then you can label them after you upload them. So it's kind of like a point-and-click interface. After you do that, which I've already done, then you can look at the labeling tag here. Right now, I don't have any unlabeled images. Everything has been labeled. This is kind of neat. You can also use human labeling for up to 5,000 images. And we can review our labels. So let's look at one of them. And finally, you can look at label statistics. So to make AutoML work, you need at least 10 images of every label, but ideally you'll have more than that, maybe 50 or 100. Okay, so then what you do is you train. The base model, remember, does only transfer learning, and this advanced model does reinforcement learning as well to find a new architecture. So let's try the base one really quick. I'm going to name this something like Spark Summit, Clouds. So you would do this, and then you would click train. And then this runs for maybe an hour or so. But since that's going to take a while, See, it's now pre-processing the images. I'm actually going to cancel this because I already built the base model and the advanced model. So we'll abort this. And then we'll go into that data set and we'll say ignore to this because we know that we canceled. It's OK. So after the training is done, we're going to do the evaluation. So I have a couple of base models and one advanced model. Let's start by looking at the base model, which was it's based on 192 images in the test set. All right, so let's look at some of these statistics for this. I'll start with area under the curve. So a 1 would be perfect, like 26% would be random. We're getting like 88%. Let's look at the advanced model and see what it's getting as well. So about 93% with the advanced model. And then for any data scientists in this room, you get a lot of the typical graphs like precision recall trade-offs, precision and a recall graph as well. So this trade-off of precision versus recall is essentially, do you care more about classifying photos correctly, which is precision, or about getting a high number of correctly classified photos, which is recall? So this graph just helps you understand that. And then there's a confusion matrix here as well. So yeah, we can see that for most of these clouds, it's doing pretty good with the advanced model. It's doing great on this type of cloud, the Cirrus. Let's go look at one of the base models as well. So maybe a little less accuracy, but this one is pretty interesting, right? The Alto Stratus gets 64% with the base model, but with the advanced model, it actually gets less than 67%. It gets 57%. So this was kind of interesting. I was kind of curious about why this was happening. So what we can do is we can actually like click on where it made a mistake, where it is this type of cloud, but it incorrectly thought it was a cumulus cloud. So let's click on that. Oops, hold on. Let me make sure I went to the right place. Confusion matrix. I'm on advanced. Let's change this to all of them. Okay, there we go. Let's go back in here, and let's find out like what's going on here. So these are false negatives. This is where the model thought this was not a Alto Stratus image, but it labeled it as one. Green means that the model correctly identified these as Alto Stratus. And true negative means our model identified this correctly not as a Alto Stratus image. So the problem here was actually that the training data was not very good. So that is basically what happened here. Like our training data was kind of not the best representative data for this type of cloud. So that's why we were getting bad results here. So the confusion matrix basically helps you drill down and find those types of problems. You can also do this. You can change this to like base, and you can compare this to advanced to see if it's actually worth paying that extra cost. And then if you go to the confusion matrix, it has like a percentage increase. So you can see that the advanced model got 12% better accuracy, maybe a little less accuracy here. Actually, wait, we might be doing the other way. Base to advanced, okay. So you can see the plus sign is showing in general, I think, I'm trying to figure out if that's the base or that's the advanced, I'm not sure. I think that maybe it's the other way around. I should have switched them at the top. Okay, so that is evaluation. Let's do a prediction really quick as well. We'll use the advanced mode. We'll do an online query. So I'm going to choose an image. Let's choose the same one. This is a cumulus cloud. We'll hit predict. and it correctly identifies it as cumulus. So here, this kind of gets rid of all the extra stuff that we were getting here. So it's more specific to your use case. And there's many ways to do this. You can use Python to do it in bulk, or a command line way to get the queries, the results back as well. If you do export, this basically lets you export your labeled data out of Google Cloud Storage. One more thing I wanted to show is, oh yeah, this is where I got the cloud image, by the way, is here's like a little application that we made using AutoML vision. So we're going to upload an image, and then this is going to kind of solve that use case. It's going to say that it's this type of cloud. They often appear on clear sunny days when the sun heats the ground directly below. So this is basically a Firebase app in Google Cloud that's using our model from here. This is what the data looks like in Google Cloud Storage. So I have a bucket. This is an object store. In here, this is my CSV file that I showed you earlier. And then if I go to like images, let's go to clouds too. And then if I go to images, this is where all the images are. I can go to a public link of one of these clouds, and you can see that these are the clouds. OK, so that is a quick demo of AutoML Vision. And like I mentioned before, this is really the first product in the AutoML series. We'll be announcing a couple more, I believe, this summer. So stay tuned to that. All right, let me switch back over to my presentation. So I have about 20 minutes or so left. What I'll do here is I wanted to talk a little bit more about convolutional neural networks and a little bit about transfer learning. Oh, this is an interesting use case, by the way, of AutoML. Google Cloud and Google Brain teamed up with the Zoological Society of London to identify species in the wildlife. So basically, what they did is the Zoological Society uses camera traps with motion and sensors, heat sensors, to take a picture every time it detects essentially motion or heat. And then we use pre-trained models initially, but all you can do there is kind of tell if it's an elephant or a tiger. So they needed the specificity down to the subspecies level. So that's where they used AutoML to start to identify specific subspecies, like that type of monkey versus that type of monkey. All right, so how does convolutional neural networks work? What's the trick here? This is kind of like the father of convolutional neural networks, Yann LeCun, who's a researcher at Facebook right now. Essentially, this is the neural network that he created, I think, like back in the 80s, I think. 1988, down there is the paper for CNNs. So there are a few building blocks here called convolutions, nonlinearity, ReLU, and then pooling. So I'm going to quickly kind of give you the intuition of what's going on here, kind of visually. So without getting into like all the math and stuff, I just want you to get a sense of how this works. And then I'll talk quickly about transfer learning. Basically, what you're doing is you're taking an image, and then you run a filter on that image. And I'll show you how that works. But that filter will give you some smaller space. And then you're going to do something called pooling. So this is called the convolution step first. Then there's something called a pooling step, and then you kind of repeat those. And at the very end, you do some fully connected layers. This is the kind of architecture I was talking about earlier on. And then at the very end, you classify this perhaps as 4 different types of animals. You can see that the output for boat is the highest, so we're going to predict that this is an image of a boat. So you stack these layers, right? So you start at the bottom, we're doing a convolution, then pooling, convolution, and then a couple of fully connected layers. This is like the old 1998 LeNet 5, that's 7 layers. These days, you can stack them a lot more. So this is another image. I think this is from Stanford. So you can see we're doing convolution, then a ReLU, then convolution, ReLU, then pooling. It's a little bit different of an architecture. But then my point is basically that I want to just explain what those three things are, the convolution, ReLU, and pooling, so you get the intuition. And another way to get intuition, I think, is just to think about what the layers are doing. Like the first layer, the first couple of layers might just be like getting some edge detection. Then you're getting like eyes and noses, and you're finally getting like faces later on. So what is that first step for convolution? Imagine that this is like a black and white picture, and like the white means that the pixel is turned on, 0 means that the pixel is turned off. So this is just an image represented as a matrix. Here is another matrix that we have x's this way and that way. Ones this way and that way. And what we're going to do is basically apply this filter to this image, but only in the very beginning of it. So what you do is you take this 3x3 grid, and imagine like that you put it on top of this part of the beginning of this larger green image, and you just do some multiplication. So you do 1 times 1, that basically gives you a 1, and then you do 1 times 0, and then you do a 1 times 1, and then you basically get the addition of all of that, and then you put the final number there. It's relatively simple. So this 0 negates that 0, there's nothing going on there. This 0 and that 1 are going to give you 0 again. So you basically just get 4 ones, and that's why we're saying that's what the feature is. So this thing over here is called a filter or a kernel. You'll usually have a bunch of them. And this on the right, which is like the output, is called the feature map. And what we're essentially doing here is we're running this filter through this image. We get a 4, then a 3, then a 4, then a 2, 4, and 3, and then finally like a 2, 3, and 4. So we're sliding this filter over our image and running this simple multiplication against each of the 3x3 grids. So this is one filter. Here's some examples of filters. Here's an identity filter, an edge detection filter, like a sharpening filter, a couple of different blurring filters. So after you do that, these are the things you can control, by the way. You can control the number of filters. You can control how much you move right every time. And you can also zero pad the filters. So after that, you essentially run the ReLU on the output. So if you get this as the output, if you had any negative numbers here, you would just basically set that to 0, because that's what ReLU does. Remember ReLU says that if any of the if the data going into the activation function is negative, then you just emit 0. If it's positive, you emit the exact same number. So essentially, if this goes through ReLU, you'll get the exact same thing back out because there's no negatives in there. All right, after you do that, you're going to do something called a pooling step. So this is the feature map we got after the convolution and after we applied ReLU. So what you do now in max pooling is you maybe take these 4 and just pick the max of it for max pooling. And then you take these 4, 8 is the max. You take these 3, 3 is the max, and 4, that's the max. So then you get this after the pooling step. There's max pooling, you can do average pooling, min pooling. Usually max pooling is what you'll do in convolutional neural nets. All right, so that's basically the trick. You do convolution, then you do ReLU, then you do the max pooling, and maybe you repeat that a few times. All right, so that's essentially the story. Now, in the last few years, this is like a pretty old CNN architecture, right? In the last few years, there's like way more interesting things going on with CNNs, like inception modules and way more complicated things. I think some of the winning CNNs are now like hundreds of layers deep. And really the challenge to figure out the correct architecture, there's really a couple of things here that AutoML does. The transfer learning part of AutoML is a pretty mature, well understood thing. You can go get a model from the GitHub for TensorFlow, that has models built off ImageNet and different vision models, and you can get them and you can freeze the bottom layers and do transfer learning pretty easily on them. I think the part that's like really interesting for AutoML is trying to do this, the advanced model creation, to search for different architectures and try to find the right one. That's probably like the real magic of AutoML, and that's really, really hard to do right now manually. So this is just saying that on the left, we're doing feature extraction, and on the very right, we're doing classification with the softmax function at the very end. One other thing that I found interesting is in Android P that's coming out later this year, CNNs are being used for adaptive battery and adaptive brightness. So with adaptive battery, what it does is it tries to basically, based on your past behavior, predict which applications you will use and basically put the rest of them to sleep, and it will only keep the ones that it thinks you're going to use next active. This has been resulting in about 30% fewer CPU wake-ups, and adaptive brightness is essentially trying to figure out, based on your surroundings, what kind of brightness you would prefer. I thought this was like a really interesting use case for CNNs, which I didn't know about. Okay. The other thing was transfer learning, so stealing pre-trained layers from an existing model. Right, this is like a pretty simple thing to understand intuitively, I think. What you do here is you go get another model that someone else trained on like millions of images, and then you freeze the bottom layers, and you're reusing the third layer here as well, but you're not reusing the fourth and fifth layer. You're adding a custom fourth layer where all the weights are like not trained yet. The third layer weights are trained, but they're mutable. These weights are not mutable. So when you now train this neural network, these weights are fixed. These are like the lower level edge detection features, like finding like lines and maybe circles, things like that. And this is a mutable layer. So this one, the weights can be altered. They can be altered a little bit. And on 4, we're just completely trying to decide the weights from scratch. This is a trick for transfer learning. This is some sample code here for TensorFlow, where we're reusing some layers and adding new layers. There's just some sample code there. Also, transfer learning is just one trick you can use when you don't have enough data. You can just go get a model from a model zoo like TensorFlow's GitHub on TensorFlow on GitHub, and not do transfer learning at all. If someone already made a model that does your use case, just use that. If you need to customize that model, you can do transfer learning. A couple of crazy newer things are called unsupervised pre-training and one-shot learning that you can also do if you don't have enough data. So check out those crazy tricks if you're interested. All right, in the last few minutes, I wanted to talk about just a couple of interesting ideas, GANs and multimodal networks. So this is not really related to AutoML, but I thought they were like really interesting things. I asked a few of the machine learning engineers and researchers at Google this week what they think the most interesting idea in deep learning has been in the last couple of years. Everyone said GANs. So this is an answer on Quora from Jan LeCun, who's a director of AI research at Facebook. Someone asked him, like, what do you think are like the most interesting potential breakthroughs in deep learning? He thinks it's GANs in the last 10 years. Also, Ian Goodfellow, who essentially is the creator of GANs, posted this a couple of days ago on his Twitter feed. It shows the progression that GANs are making in generating fake images. You can see in 2016 that it's like all jumbled up. You can barely tell it's a butterfly. And these are like mutant dogs in 2017. And this year, you're like starting to get to like pretty photorealistic fake images. And maybe in the next couple of years, this will become like quite mature technology. So Ian is the guy who like essentially had the idea of GANs in a bar in Montreal. His idea was, it came up when some of his friends were trying to figure out how a computer can create photos by itself. And the idea was basically to pit two neural networks against each other. So a GAN basically gives machines something like imagination. The way it works is you have a generator network and a discriminator network. The the generator network basically creates output, like an image or some handwriting. It sends that to a different network, the discriminator network, that judges the output and tries to decide if that image was like real or fake. And then it reports the results back to the generator network, and it also says why it thinks the image might be fake. Then the generator network adjusts its parameters for creating new images till the discriminator can no longer tell if it's real or bogus. So this is usually a deconvolutional network for the generator, and then this is a convolutional network for the discriminator usually. So this can potentially be applied for a lot of interesting use cases. One of them is to maybe make generate fake medical records that are almost as good as the real thing, or generate images from text descriptions. I don't know, like this is just an interesting field. I would follow this if you're interested in deep learning. This is where some of the biggest breakthroughs might happen in the next year or two. The other kind of crazy thing I think is this, multimodal neural networks. So I think it was last year that Google published this paper, one model to learn them all, and one of the deep learning engineers, I think he was the head of deep learning at Tesla for a while, he said this is another step in Google's attempt to turn all of itself into one big neural network. So what this is it's a single neural network trained to do multiple tasks. It was trained on Washington Street Journal speech corpus, on ImageNet and image captioning via the COCO dataset, and also on multiple translation tasks between 3 languages, and also parsing, like getting the grammar out of text. This neural network has convolutional layers, an attention mechanism, like from an RNN, and sparsely gate layers. This is a paper. This is what the architecture looks like. It has some funky things in it. And this is just performance that kind of blew me away. So on ImageNet, it gets 86% accuracy. State of the art is like 95% when the paper was published. This is translation from English to German. So it gets pretty close to state of the art. This is English to French. So the crazy thing is that Google didn't actually invest much time in tuning the hyperparameters of the multimodal network. So Google thinks that, we think we can get this very close to state of the art. So we would have one architecture that can actually do like, translation, object detection, and grammar parsing. So I think this was just like a pretty crazy, interesting idea that came out in the last couple of years. All right, so that's really it. I think I have 2 minutes, so maybe I'll end the actual talk, but I'm going to hang around here to take any questions offline if you guys have any. Cool, thanks for coming.